Hello, Burden.
Hello.
Oh, thanks.
Pretty good. How about you?
Yeah, going fine. Hello, Jeremy.
Hello.
We wait for Curtis. I think he'll catch up. We have homework 9. You. The last problem involves a result that we will be deriving today. But even by any chance, if I do not reach the result, but I'll make sure that I'll do it, and you guys usually allow, you have agreed to allow me to take some extra minutes if needed. But even otherwise, it gives a result and then you can analyze it. So it should not affect the homework as such. So let's make it due on Monday. Final exam. We were discussing the what will be the electric potential, and eventually we want to talk about the electric field and magnetic field due to a uniformly moving point charge. So uniformly moving point charge. And we did all the or we found the retarded time for this purpose. So let's remind ourselves of what we were doing. There's a positive charge moving with velocity v, and we chose it to be going along the z-axis, so that x prime and y prime is 0. So this is the position of the charge q, let's say, as a function of, let me say, as a function of t prime. It's okay to say t also, that's okay. 0I hat plus 0j hat plus, we said, v times t or v times t prime. That's your position as a function of time. Velocity of this charge as a function of time stays the same. It's uniformly moving, so it has to stay the same. It is not a function of time. The equations that govern this motion is the wave equation, and the source of this wave equation is equal to the charge density R. Where the charge density is delta functions, correct? So let me try to squeeze the charge density in here. Since it will be r prime t prime, let me write it as r prime t prime. So that's q times delta of x prime, delta of y prime, and delta of z prime minus the position, which is z minus vt prime. That just fits in. And the current density, J, would be just velocity times the charge density. So if I know this, I can immediately write down the current density. Also, if we are talking about the vector potential, A of RT, then instead of rho, we have J. That's both satisfy the same equations. For evaluating such an equation, we said that, okay, let's actually talk about a charge that exists only at a certain time t prime, or what is the contribution due to a charge at position r prime at time t if the signal charge existed at t prime. Right? So we said that's given in terms of the Green's function, or you can say the electric potential due to a point charge, which is a function of time. And that's given as t minus t prime minus 1 over c times r minus r prime divided by 4 pi times r prime. So this is at one instant of time. If we want all the instants of time and all charges to be added up, then we have to do a superposition principle. This time, a superposition even in time. Right? At each time, the charge contributes a certain signal, and it's a collection of them because it could be the same charge, but since it is coming from the past, it could add up more than once if necessary. In our case, it will add up only once. So this comes out to be equal to 4 pi epsilon naught. Integral over time is the new quantity, and we do the old version too. So this is d cube r prime, and the delta function t minus t prime. We call this t minus t prime, and then r minus r prime over c divided by 4 pi. And we have rho of r prime comma t prime. Same thing works for vector potential also. Let me not write that down here. Vector potential, replace this with g. We evaluated this for the case we are considering, and we showed that this comes out to be equal to, we can do the r prime integral trivially because each one of the three delta functions in there, and we learned that this is equal to t minus t prime minus 1 over c, and this was x squared plus y squared c minus vt prime divided by the distance itself was the same quantity that it is inside the argument of the delta function. That's your electric potential, and we said, oh, that's not a trivial evaluation of delta function. That's a function inside. That's a function existing inside the argument of delta function, but we evaluated it so that we called f of t. So we said, let's say f of t prime is equal to t minus t prime minus 1 over c square root of x squared plus y squared plus c minus vt prime squared. And this gets contributes, this integral contributes whenever f of t prime is 0. And at that point, there were two solutions. And we said that for causality reasons, only one solution is allowed, and we call that the retarded time. Basically, that's the signal, that's the delay in the signal because the signal has to travel a certain time. You post a normal postal mail in Carbondale today, it will reach Chicago after a few hours, even if it goes very fast. So that delay is what we're talking about, and here it is traveling at the speed of light. We showed that when we are evaluating this, there is a derivative of this function is relevant. So derivative of this function is -1, and it's a magnitude of that shows up. So it is actually -1 plus. And I take the derivative, it hits this velocity v over c and c minus vt prime divided by x squared plus y squared, same quantity. If I'm taking the magnitude, I should switch the sign of this. This is actually the actual derivative, but notice the numerator will always be less than the denominator because the denominator has x squared plus y squared plus the numerator, the square of the numerator itself, and v over c is always less than 1. So I can say if I'm taking the magnitude of this, I just have to switch the sign. So it's 1 minus this quantity. Whenever this is equal to 0, we found the solution to be, we'll call it the retarded time, T of R we showed was equal to T of R was equal to, let me write it on the other side of the book. I need more space. Okay. So the retarded time was equal to T minus V over C and Z over C minus x squared plus, write it as 1 over C times x squared plus y squared plus no, there is a 1 minus beta squared, right? And this whole thing divided by 1 minus v square or 1 minus beta square. Beta is v over c. It seems like a trivial statement at this point, but we will need this. So I'm going to multiply this out and rewrite this in the following form. It will help a lot in processing one of the equations that follow. Plus z minus vt squared is equal to t minus v over c, z over c. Basically multiplying this and putting it back there. And I'm mixing things up. This is beta is v over c, so this is v squared over c squared. So this should be beta in that data point. So let's note this relation. This will be important. Let's just start that. And if we use this, this is where we were actually last time. If we use this in the scalar potential, what I get is scalar potential 5RT. If I were to evaluate that delta function using our identity, we have 1 over 4 pi epsilon naught. So the identity would be dt prime minus infinity to plus infinity. There is a delta function that sits in there, but now we replace that with just the contribution from the retarded time divided by, which can be a t prime. And we have x squared plus y squared plus z minus vt prime squared. Remember, delta function evaluation involves replace t prime with tr. But we also need to have df over dt prime evaluated at t prime is equal to t of r, and then take the magnitude. Right? That's your identity, the big delta function that we wrote earlier that can be replaced with this, and that was our identity. Let's evaluate this. It's immediate. We just have to replace t prime with tr everywhere. And that's equal. So now we have all the integrals done, so we just have to manipulate our relation from this point on. So that's equal to 1 over square plus y square plus z minus v tr. Now t prime gets replaced with tr. Right. And 1 over the derivative of the function f, that's nothing but 1 minus the same expression except that there is a beta this time. I will write this as b over c still. So b over c z minus vtr divided by x squared plus y squared plus z minus vtr. That's your electric potential. It is a complete closed form solution. But let's process it. It can be written in a much simpler way. So let's process this. Let's multiply, or a relatively simpler way. It cannot be done more than what the relativity does take the symmetry in x, y, z. This can be taken into the bracket. So let's do that. So it's 1 over 4 pi epsilon naught. And what we have is square plus y square plus z times z minus vtr square minus of v over c times, let me actually in this term also multiply and divide by a velocity c. That helps because I can always divide by 1 over c, and then there is a 1 over c there, right? So that's perfectly fine. And let me do the same thing here, 1 over c here and 1 over c there. That's just looking into the next step that we are going to see. I think that's so. When I do this, so these two cancel out, and I have v over c times z over c, and then minus v square over c square, so which is plus v square over c square t of r. Okay. Remember again what this is. This is actually the function f of t r. So I think I should go back here and show you. Notice that if this was equal to 0, so whenever t prime is f of t prime is equal to 0, that means t minus t r this time, whenever it's 0, it is the retarded time, is exactly equal to the square root quantity. So we can replace 1 over c times the square root with t minus t r. So let's do that. So I do that. So this whole quantity is just t minus t r. You can actually explicitly expand and do the same thing, like substitute d of r and do that. But that's tedious. Here we're using tricks to get the same expression. So this is 1 over c in the numerator. So that's 1 over c. And there should be a charge q, right? Everywhere. So there's a charge q. Here. This charge q, 1 over c times t minus tr minus v over c, z over c plus v square over c square times t of r. Let me rewrite that again. So that's q over 4 pi epsilon naught, 1 over c in the numerator. So that's t minus v over c times z over c. That was a, and minus 1 minus beta square times t of r. And if you notice, that was exactly the the expression we had earlier, we had starred that, right? We had made a star mark on that. That's exactly that. Let me show you that. So that's the starred equation. That's why I can replace that denominator in terms of that. So everything looks as close to a point charge at a static point charge that you can have. So let me use that. So the electric potential then becomes so the 1 over c then cancels out. So this is q over 4 pi epsilon naught. And we have 1 over x squared plus y squared times 1 minus beta squared. Notice this is like a contraction, right? 1 minus beta square is divided by gamma square, but it seems like it is x and y that is contracted. We will look into that very close, very soon. That's z minus vt prime. Sorry, vt this time, vt squared. So that's the electric potential due to a point charge moving with velocity v. Everything seems to be right or very intuitive here. For example, if you were going or if signals were going instantaneously, then beta would be 0 because c is going to infinity, and you will just replace the position of the charge as it is moving, right? So this part is simply moving the charge as it is moving. But this is a contribution from relativity. That means it is saying that x and y are going to get contracted as far as the electric potential is concerned. So let's see how this goes about. For that purpose, let's calculate the electric field. But before that, what is the vector potential? Vector potential is simply velocity multiplied by the scalar potential in this case, because what happens is that if you follow the J, almost everything goes through except that there is a V times K hat right in front of it. So pretty much it's exactly, I can say, let me just make sure. Second. Yeah. So what we have is the scalar potential is 1 over epsilon naught. Rewriting this, I have this on this board space. Plus z minus vt squared. And the vector potential is equal to mu naught over 4 pi, because to start with the current density, we'll just have a constant velocity vector in front of all the integrals, everything goes through, and you get velocity in the k direction divided by x squared plus y squared times 1 minus beta squared plus z minus vt the whole square. So that's your vector potentials now, but we want to actually go further and calculate electric and magnetic field. Any questions at this stage? Remember that if you were to transform, like you have your z prime and ct prime is equal to gamma, beta gamma, beta gamma, gamma times z times ct. And if you were to do this for electric potential, also behaves the same way. So you can also do gamma times phi over C, and then the vector potential. But also remember that they are dependent on R and T. So how do they work? That's equal to phi over C times R comma T here, and then A R comma T. Notice the difference between, this is not R prime and T prime. I would like it to be R prime and T prime. So the function scalar potential and vector potential itself transforms like a Lorentz vector, and then from that point on, I have actually transformed the inside the variables that is inside the function again using this. So it's a function of a function, so there are Lorentz transformation to be done inbuilt inside also. And if you do all that, one can actually do this exercise separately, that you do the transformation from here and get here, and eventually you will get exactly this. For a moving charge, the electric potential and vector potential looks like that. But once you have that, let's start with the electric and magnetic field. Electric field is negative gradient of phi minus d by dt of A, and magnetic field is the curl of A. That's not very difficult because these are all derivatives with respect to x, y, z, or t, and they are all of the same form. Right? So whenever you take a derivative of a square root, it becomes 3 by 2, right? Power goes to 3 by 2, and then you have to hit the argument. So you get 2 times x, for example, when you take the x derivative, and you also will have a 1 minus beta square. So let's try to put all this together. One can almost read through this. So let me do one exercise first, just the d by dx, and then d by dx of phi will be equal to, in the board space, yes, will be equal to 1 over 4 pi epsilon naught. That will be a minus 1 by 2, so that's minus 1 by 2 because of the power. And in the denominator, this becomes x squared plus y squared times 1 minus beta squared plus z minus bt, the whole square raised to 3 by 2. And in the numerator, now I have to supply the derivatives of this piece here. So that's 2 times x times 1 minus beta squared. But there is also this negative sign in here that gets rid of the negative sign. Factor of 2 cancels out. And this will happen for y also. And z will not get this 1 minus beta square. When you do it with respect to z, you just miss this 1 minus beta square. When it is coming with respect to time, it's very similar, except instead of this 1 minus beta square, it gets this minus v out there. So if we put this all together, the electric field will be equal to you can see the x 1 minus beta square coming in. So this is 1 over 4 pi epsilon naught. The denominator stays all raised to 3 by 2. Plus z minus vt, the whole square 3 by 2. And x I hat times x times 1 minus beta square plus j hat times y times 1 minus beta square. When it comes to z, there is only z minus vt that shows up, right? So that's k hat times, there's only z minus vt. no 1 minus beta square, but then there is a time derivative with, or there is a derivative with time, which actually gives you a minus b over c, but then when you're taking the derivative with a, there's already a velocity in there. So all that contributes to another piece in here. So that's plus k hat, because vector potential was in the direction of k hat. So that's plus k hat, again, so z minus vt, and there is a minus beta square that shows up there. So together, this piece and this piece again give you a 1 minus beta square there. So they all nicely fit in. And how much is this? This is equal to a factor of 1 minus beta square multiplying out. Remember, 1 minus beta square is 1 over gamma square. If you want, that's perfectly fine. That's one way of looking at it. I hat times x plus j hat times y plus k hat times z minus vt. Notice that this is the direction of the electric field, and direction does not change at all. There is no change in the direction if you were to think of it from the classical sense or non-relativistic sense, because this is just changing the position of the charge, shifting it by Vt, but direction stays x hat, y hat, and the origin shifted. But the magnitude of the electric field, which is decided by the denominator, it should be 1 minus r squared, but that's skewed actually. X and y is scaled by the Lorentz factor, but the z direction is not scaled, or at least it is scaled in different form. It is not scaled the same way. Both get scaled because there is this 1 minus beta square. So that's your electric field. We will draw this in a minute, but let me also get the magnetic field. Magnetic field is a curve, and it is relatively straightforward because even though it looks like it is the curve, the vector potential, whatever is the direction of it, it's a constant. I can pull it out, and it is basically z crossed with the divergence of the scalar potential. And that comes out to be equal to, so let me, it will be in the phi hat direction still. So it is beta. Oh, so that is 1 minus 1 over 4 pi epsilon naught, right? So I intended to write that. There's beta times 1 minus beta square times mu naught over 4 pi and it's in the direction of phi. So it's phi hat and the same factor, square plus y square 1 minus beta square plus z minus vt whole square is 3/3. And factor of velocity, let me check that. Q, right? Yeah, that's all. Yeah, so let me actually, I should, because there is a dimension here, right? So this is Q times V if you want. So it's x squared plus y squared square root of that. That's a radius rho in that sense. So that's Q. Okay, that's your magnetic field, which comes about exactly the same as the electric field I talked about. So how does it look like? And I will also explain. If you were to plot this, So you have this charge, or at least describe this using a diagram. So you have this positive charge, which is moving, I said earlier, upwards. Let me draw it horizontally, easier to draw. Let's have a scale. So this is your z direction, that's your velocity v. So that's your z direction. If it was at rest, let's have the scale to be that's your scale, and that's your x direction. Now it does get so what happens is that it gets stretched out. So it goes up in the x direction. So let me say this will be electric field here will be larger than the electric field that should have been the case for if it was not moving. And the electric field in this direction gets squeezed. So let me get rid of the velocity. So that's the electric field in this direction. And this forms an ellipse. And this gets squeezed, right, symmetrically on both sides. That's your electric field in the z direction, which is getting squeezed in there. So let's try to see how we can see that squeeze in there. So let's look for the at time. Let's set time t equal to 0. It is moving, but you're setting right at time, like it could be going from minus infinity to plus infinity. I just need a snapshot, so I take a snapshot at t equal to 0, right when it was crossing you and you set your time t to be equal to 0. At time t equal to 0, the x component of your electric field, and at which point are we calculating? Let us calculate it at a distance x away, right? And z is equal to vt, so that z is equal to 0. So x is equal to x, then y is equal to 0, z equal to 0, and time equal to 0. So let's calculate that most of the quantities go away, and what we have is there is 1 minus beta squared. I want to capture how much it is squeezed or scaled out. So that's I hat times x times 1 minus beta squared in the numerator. And then in the denominator, also I have x squared or 1 minus beta squared, right, raised to 3 by 2. So we have, and there's a charge q. I keep forgetting the charge q. So this is q over 4 pi epsilon naught. And I had over x squared, right? That's how our charge would have been if it was all at x rest. But now we have 1 minus beta squared times 3 by 2. And there is a factor of 1 minus beta squared in the numerator. So that's 1 minus beta squared, which is gamma, right? So let me write that as gamma. So gamma, remember, is always greater than 1. So that x component of the electric field gets dilated by a factor of gamma. What about the z component? And y component will do exactly the same. So what happens to the z component? And let's do that as x is equal to 0, y is equal to 0. So we are going a little ahead of, so charge is here at time t equal to 0. So we are going slightly ahead of that and seeing what is the measurement, how much electric field contributes in there. So that's z, and that's time t is still 0. That's q over 4 pi epsilon naught. And x, y, z is all 0. So we have k hat times z times 1 minus beta square divided by, this time it is z square raised to 3 by 2. Right? That's all. And that's equal to q over 4 pi epsilon naught k hat over z square. That's what we would have if it was all static. But now we have 1 minus beta square, which is in the denominator, right? So that is a gamma square in the denominator. So the z components not only get contracted, they get contracted by a factor of gamma square, much more than what it's x component got dilated, while z component got contracted, but not by factor of power in that sense. We can also do this for the magnetic field. So electric field is getting squeezed as we are in the plane perpendicular to the direction of motion. And when it comes to magnetic field, what's happening is that I'll show it pictorially because we already have that expression there. So magnetic field, remember, if it was a current carrying wire, then you will have the magnetic field in this sense. So that's your magnetic field lines, but then they get smaller. They're less powerful in that direction. And this gets, so same thing here and here. And here also we can try to calculate what is the component by what factor of gamma Lorentz factor is this getting contracted or dilated. And I'll leave that as an exercise for you guys. What I want to do in the last 5 minutes is I want to talk about, we have this electric field. This is part of your homework also. And I want to take the extreme limit where beta is actually going to infinity. So if these charged particles are extremely going fast, then there is this flashlight effect. You don't call it flashlight. Like what is happening here is that is positive charge going with velocity v. All the electric field lines fold itself to be in this direction. Like I shouldn't say they fold itself. There is still remember the directions are all the same. It's just that the this is amplified so much that this is this way, and this is all shortened significantly. That's how it is. So as you go faster and faster, this gets dilated more and more, and all these components are getting shorter and shorter. And one would like to consider what happens in the extreme limit. What is the extreme limit when v really tends to speed of light? Of course, the electron cannot go at the speed of light, but let's take this limit anyway. And remember that 1 minus beta square in that case tends to 0. So if we take that as a factor of epsilon, so we say that this is actually epsilon square, and let's analyze what is going on. So the electric field expression for that case is equal to 1 over 4 pi epsilon naught. And there is this epsilon square sitting everywhere. So that is epsilon square, because that's 1 minus beta square. And that is x square plus y square times epsilon square. plus z minus vt square raised to 3 by 2. And there is a direction associated with this. Let me call that n hat. Am I in the board space? Yes. And in your homework, the idea you have to use is that this is sitting there and this is sitting here. Also, actually, this is epsilon, right? Or 1 minus beta square is epsilon square. Yeah. And you have to use the identity that, is it epsilon or epsilon square? I don't remember the homework. Check if I'm using epsilon or epsilon square. It might be epsilon also. If it is epsilon, this is epsilon and that's epsilon. Check on that in your homework. But the idea is that you have to first show that if it is epsilon over, if it is, let's say, what's the variable I should use? Say t squared, and that's 3 by 2. And in the limit epsilon tends to 0, you have to show in your homework that this is actually a delta function as a function of time t. And for that, what you do is that first set t is equal to 0 and show that that's divergent. If t is equal to 0, then this is epsilon over, so there is more epsilons in the denominator, so that means it is divergent. But if it is t is very close to 0, but not really 0, it's not equal to 0, then numerator is going to 0. In that case, that whole function goes to 0. So you show that that's actually a delta function, and in that case, if you use that relation, you get that the electric field is completely in this plane. So in that extreme limit, all these components goes to 0 in the direction of motion, and only the components that is perpendicular to that survive, and not only survive, they actually go to an extreme version, and that is the feature of delta function, and electric field comes out to be 1 over 4 pi epsilon naught, and you have to show that this is actually rho hat over rho, where rho hat is xi plus yj, and rho is x squared plus y squared, which is only in a plane. And there is this delta function showing up, which is delta of z minus ct. That means the charge is always moving with respect to the point it is moving. So try to interpret that and try to draw these diagrams and try to understand that it will give you a little bit of insight of what's going on. And there is a lot of literature and diagrams available all over the internet to search over it, and hopefully it is useful. And I think I finished it on time too. So thanks. So
Thank you. Have a good weekend.
Gordon, questions?
No, I'm just finishing writing this stuff down.
Okay, good. How is it going, Gordon? Any comments on the on what we're doing here?
So far, I'm good.
Have you seen this anywhere else before by any chance? Probably not, right?
I'm not sure. Probably, yeah, probably not.
Yeah.
All right. Have a good weekend.
Okay, you too.
Thank you.
Gordon.
Bye.